You've probably seen the date already, December 19th. Circles on thumbnails, arrows pointing at Earth. A strange name in the title 3I, Atlas, an object from interstellar space, and a question nobody seems to answer clearly. What actually happens when it swings past our planet? Is this a real threat? A misunderstood event? Or just another recycled doomsday story with better graphics? Tonight on Sleep Astronomy, we're going to strip away the drama and look at the physics. If you like calm, honest dives into scary-sounding space news, a quick like and subscribe helps others find us too. Now, let's start with what 3I Atlas really is. December 19th, 2025. Circle that date, because on that day, you are going to witness an event only 3 generations of humans have ever seen. An object from beyond our solar system, passing within striking distance of Earth. 3I Atlas is currently screaming toward us at about 7,000 miles per hour, and it defies everything we think we know about space rocks. It is accelerating when the math says it should not, and it is releasing materials that do not fit our current models of how comets behave. In exactly 25 days, this object crosses Earth's orbital path at a distance closer than the Moon. Every major space agency, NASA, ESA, and every primary observatory on the planet has their telescopes locked onto this interstellar intruder. But the major headlines are missing the point. The fundamental physics behind this object do not fully add up. You need the unfiltered scientific breakdown of what December 19th truly means. The exact orbital mechanics, the statistical collision probability, the detection systems that nearly missed it entirely, and the brutal truth about what it would take to stop something like this if the worst-case scenario were upon us. To understand the situation, we need to rewind to October 13th, 2024. That is the moment astronomers first registered its presence. It was nothing more than a faint, blurry smudge of light moving slowly through the constellation Serpens. Initially, 3I Atlas was filed as just another comet. Yet, within 48 hours of detailed tracking, a disturbing conclusion was reached. This object did not originate here. Its path, its trajectory, told a story that caused astronomers globally to pause their work. The data was undeniable. This thing was moving at 31 kilometers per second, or roughly 19.3 miles per second relative to the Sun. This speed is far too high for it to be bound by our solar system's gravity. It was confirmed as a visitor from interstellar space, making it only the 3rd such object we have ever confirmed in the entire span of human history observing the cosmos. Pause and consider that for a moment. Humanity has been watching the night sky for thousands of years. We have catalogued literally millions of asteroids, comets, and other space rocks. But interstellar objects that started their journey around another star, we have confirmed precisely 3. The first was Oumuamua in 2017, a cigar-shaped mystery object that left scientists completely baffled when it accelerated without any visible jet or propulsion. The second was 2I Borisov in 2019, a more conventional comet that at least followed the rules and behaved exactly as our scientific models predicted. And now we have 3I Atlas, but this one introduces a new level of complexity because it does not fit neatly into either of the first 2 categories. Dr. David Farnokia from NASA's Jet Propulsion Laboratory articulated the problem perfectly when the initial data arrived. He stated that we are seeing outgassing activity, the release of gas and dust, which is entirely consistent with a comet being heated by the Sun. However, the overall acceleration profile is off by a factor we cannot currently explain. Simply put, It is spewing material like a normal comet should, but the way it is speeding up does not match the force provided by the gas jets we observe. Something else is providing a push, and our current understanding of physics has not yet identified the source. Let's focus on the distinction that makes an interstellar object fundamentally different from every other object we track. Every single asteroid, every comet, and every tiny dust grain you hear about in our solar system is gravitationally trapped here. They are bound by the sun's gravity, orbiting in elliptical paths that bring them back around, sometimes taking millions of years to complete one loop. Interstellar objects, on the other hand, are on a hyperbolic trajectory. Imagine a sharp, curved path that sweeps rapidly toward the sun, whips around it once, and then accelerates back out into the galaxy, never to return. That is the path of 3I Atlas. It began its journey somewhere far beyond the gravitational reach of our sun, traveling through the deep, frigid void of interstellar space for a period we can only guess at. Now, it is cutting through our immediate cosmic neighborhood on a one-way trip. The required math for this journey is enormous. To carry the sheer velocity that 3I Atlas currently possesses, it must have been violently ejected from its home star system. This likely occurred during the extremely chaotic early formation of its planets, when intense gravitational interactions were flinging objects around like cosmic billiard balls in space. Imagine being a massive chunk of ice and rock, simply orbiting your distant star, and then being forcefully kicked out into the freezing darkness at speeds of tens of thousands of miles per hour. That is the origin story of this object. It has been wandering the galaxy ever since, until the gravity from our own sun bent its path just enough to bring it screaming through our solar system. This leads us to the part that truly excites and slightly unnerves scientists. We can calculate the orbit of 3I Atlas with extremely high precision, thanks to data gathered by observatories like the Asteroid Terrestrial Impact Last Alert System, or ATLAS, which is what the acronym stands for. Astronomers have mapped its exact path, and the results are significant. On December 19th, 2025, the object will cross Earth's orbital plane at a distance of approximately 0.027 astronomical units. To make that number meaningful, 1 astronomical unit is the distance from the Earth to the Sun. 0.027 astronomical units converts to roughly 2.5 million miles. Before you start to relax, let us put that distance into a cosmic scale. The Moon is only about 239,000 miles away from us. So yes, 3I Atlas will pass us at a distance about 10 times farther than the Moon. But in cosmic terms, that is incredibly close. That is what astronomers call threading a needle. NASA officially classifies any object passing within 0.05 astronomical units as a close approach. This interstellar visitor is coming in at less than half that distance. Here is the most critical detail. We almost did not see it coming. The Atlas survey system is specifically designed to detect near-Earth objects that originated here. 3I Atlas was spotted relatively late because of its inbound vector. It was approaching from the general direction of the Sun. This means that for many weeks, it was completely hidden in the glare of the solar light, invisible to virtually all ground-based telescopes. By the time it moved into a position where we could track it properly, it was already deep inside the solar system. If this object had been on an actual collision course with Earth, we would have had perhaps 3 months of warning, 3 months to detect, confirm the threat, calculate a response, and act on an interstellar object traveling at 7,000 miles per hour. Let's quickly compare this detection to our previous interstellar visitors. Oumuamua was detected after it had already made its closest approach to the Sun. We quite literally caught it on its way out of the solar system. By the time scientists realized what they were looking at, the window to study it in detail was rapidly closing. It is now over 5 billion miles away and continues to accelerate permanently beyond our reach. 2I Borisov gave us significantly more time. We tracked it for months, capturing detailed images, analyzing its makeup, and confirming it was a comet from another star system based on its unique chemical signature. Specifically, it had an unusually high concentration of carbon monoxide that did not match the makeup of any comet formed within our solar system. But 3I Atlas is giving us the best observation window we have ever had with an interstellar object. And what we are seeing is fundamentally strange. Detailed spectroscopic analysis, which is simply breaking down the light reflecting off the object to determine its chemical components, shows that 3I Atlas is releasing water vapor, carbon dioxide, and carbon monoxide as the Sun heats it up. This is entirely normal for a comet. However, the measurable rate of outgassing does not match the acceleration we are measuring. According to the basic laws of physics, when a comet releases gas, those high-speed jets act like tiny, natural rocket engines. Pushing the comet slightly off its predicted course, we can calculate exactly how much thrust those jets should produce based on the amount of material being released. And for 3I Atlas, the numbers simply do not add up. It is accelerating roughly 15% faster than the observed outgassing alone can explain. Does that sound familiar? It should. That is nearly the exact same unusual behavior observed with Oumuamua. At the time, scientists proposed dozens of theories for Oumuamua's unexpected acceleration. Maybe it was rotating in a strange way. Maybe it had an extremely unusual, non-uniform shape that somehow amplified the natural rocket effect of the gas. Perhaps it was coated in a super-reflective material that allowed sunlight to push it harder than expected. Some researchers, such as Avi Loeb from Harvard, even floated the highly controversial idea that it could be an alien probe using light sails for propulsion. The scientific community generally dismissed that last idea, but the difficult scientific truth remains. We still do not have a single, fully satisfactory explanation for Oumuamua's acceleration. And now, 3I Atlas is exhibiting the same unexplained behavior. What are the chances that 2 out of the 3 confirmed interstellar objects we have ever seen behave in ways that fundamentally break our existing scientific models? Either we are missing something critically important about how these objects work on a chemical level, or interstellar space is full of weird phenomena we have never encountered before. Either option provides significant, unsettling implications. So, where exactly did this cosmic wanderer come from? Tracing its path backward through the galaxy is comparable to running a long, complex movie in reverse. Astronomers at the European Space Agency have done precisely this, using the object's current velocity and calculated trajectory to determine where it was millions of years ago. The results indicate a general region in the direction of the constellation Aquila, but pinpointing the exact star system that birthed it is effectively impossible. Space is vast, truly incomprehensibly vast. Even traveling at 31 kilometers per second, 3I Atlas could have been traveling for tens of millions of years before reaching our solar system. Its parent star could now be hundreds of light years away, drifting in a completely different sector of the galaxy. But here is the confirmed takeaway. This object survived the journey. Think about the implications of survival. Interstellar space is not empty. It is constantly permeated by intense radiation, cosmic rays, and the occasional high-speed collision with tiny particles. For 3I Atlas to still be outgassing, to still have volatile ice intact after potentially millions of years in the freezing void, means it is either incredibly well preserved, perhaps protected by a thick outer crust, or it is relatively young in cosmic terms, meaning it was ejected from its star system not long ago. That tells us something highly fascinating about the conditions and processes operating between the stars. As December 19th approaches, every major observatory on Earth has scheduled time to watch this event. The Hubble Space Telescope, the James Webb Space Telescope, and the European Southern Observatory's Very Large Telescope are all going to be pointed directly at 3I Atlas during its closest approach. Opportunities like this are exceptionally rare, truly once in a generation. We are looking at a chance to study an object from another star system up close, gathering data that could force us to rewrite our fundamental understanding of how planetary systems are formed, what materials are ejected into interstellar space, and what truly exists in the deep darkness between the stars. But before we get completely absorbed by the science, we must address the question that is at the front of everyone's mind. What if the calculations were wrong? Let's run the absolute nightmare scenario. For a moment, let's completely disregard the 2.5 million miles of safe distance we've been promised. Imagine the trajectory of 3I Atlas was miscalculated by only a fraction of a degree, a minuscule error in its approach angle, perhaps due to an unforeseen gravitational nudge from Jupiter or another distant planet. Suddenly, December 19th is no longer a stunning celestial spectacle. It becomes an unimaginable catastrophe. What, precisely, would happen if an interstellar object traveling at 31 kilometers per second, or roughly 19.3 miles per second, slammed into Earth? First, we need to establish the size of the object we are dealing with. Based on its measured brightness and the observed rate of outgassing, astronomers currently estimate that 3I Atlas is somewhere between 300 meters and 600 meters in diameter. We will use a midpoint for our scenario, calling it roughly 450 meters wide, or about the height of the Empire State Building in New York. Now, 450 meters might not sound enormous when compared to the asteroid that caused the extinction of the dinosaurs, which was estimated to be about 10 kilometers across. But here is the critical difference in impact physics: velocity. The impactor that ended the Cretaceous period, the one that created the Chicxulub crater, struck Earth at approximately 20 kilometers per second. 3I Atlas is moving significantly faster, at 31 kilometers per second. When dealing with impacts, velocity matters exponentially more than size. The kinetic energy of an impact, which is the destructive potential, is calculated using the formula 1/2 multiplied by the mass multiplied by the velocity squared. That squared component, the v squared term, is the factor that drives the destructive power. Double the speed and you quadruple the energy. At 31 kilometers per second, a 450-meter object carries the kinetic energy equivalent of roughly 3,500 megatons of TNT. To put that scale into perspective, the largest nuclear weapon ever detonated in history, the Soviet Tsar bomber, in 1961, yielded 50 megatons. This single impact would be 70 times more powerful than the Tsar bomber, or the equivalent of 70 Tsar bombers detonating simultaneously in one location. Let's walk through the hypothetical consequences, hour by hour, if 3I Atlas were to hit Earth. And here is where the terrifying details emerge. The precise location of impact is enormously important. In scenario 1, the object hits land, Let's assume, purely for scale, that it strikes the central United States, perhaps somewhere in Kansas. The moment of impact is almost impossible to comprehend. The object is instantly vaporized, along with several cubic kilometers of rock and soil beneath it. A colossal fireball expands outward, superheated to thousands of degrees Celsius, incinerating everything within a 30-mile radius in less than a second. The shock wave that follows travels at supersonic speeds, instantly flattening buildings, infrastructure, and forests out to distances exceeding 100 miles. Windows would shatter across 5 states. The seismic shock would register as a magnitude 7.5 earthquake, easily felt as far away as New York and Los Angeles. But that is only the first hour. Hour 2 is when the effects begin to become global. The impact has thrown billions of tons of debris into the atmosphere, vaporized rock, fine dust, and ash. All of this material is superheated and rises rapidly on massive convection currents. Within 2 hours, this rising debris cloud begins spreading across the entire northern hemisphere, starting to visibly block the sun's light. Surface temperatures immediately begin to drop, not yet catastrophically, but noticeably. Meanwhile, the powerful shock wave traveling through Earth's crust has triggered secondary earthquakes along existing, vulnerable fault lines far from the impact zone. Emergency services across the entire American Midwest would be completely overwhelmed and collapse under the sheer scale of the devastation. By hour 24, the full atmospheric effects kick in globally. The massive debris plume has encircled half the planet, and the sunlight reaching the surface has decreased by 20%. Agricultural scientists are already running catastrophic crop failure models. If this level of sunlight reduction continues for weeks or months, widespread famine is inevitable. Global average temperatures would have already dropped by 3 degrees Celsius. Since this impact is set in December, the northern hemisphere is already cold. Now it is plunging rapidly toward a premature ice age scenario, and we have not even accounted for the massive secondary fires. The initial thermal radiation ignited countless wildfires across a radius of 200 miles. Those fires pump even more soot and ash into the atmosphere, compounding the cooling effect. Hour 48. The global economy is in utter freefall. Supply chains are shattered completely. Panic buying has emptied food stores across 3 continents. Governments are declaring martial law. And here is the nightmare within the nightmare: the impact crater itself. It is a still glowing hellscape, roughly 5 miles wide and a mile deep, continuously radiating heat. Geological surveys confirm the worst fears. The impact fractured the continental crust deep enough to expose mantle material. Magma is actively welling up. What was once rich farmland in Kansas is now an active volcanic zone that will smolder and vent for decades. Hour 72. The debris cloud has fully encircled the entire planet. Sunlight is reduced by 40%. Global temperatures have dropped 8 degrees Celsius in 3 days. Coastal cities, surprisingly, are dealing with an unexpected crisis: tsunamis. These waves are not from the impact itself, but from massive landslides triggered by the seismic shock waves along the continental shelf. Entire sections of the continental shelf off the coast of Norway, for example, could collapse into the ocean, sending significant waves across the North Atlantic. The death toll is climbing rapidly into the millions, and we are only 3 days into the event. Now, the critical scientific question: would this be an extinction-level event? Probably not. For humanity as a species, we are highly adaptable, and we possess technology. Frankly, 3,500 megatons, while catastrophic is not the scale of the Chicxulub impact. The dinosaur killer was estimated to be in the neighborhood of 100 million megatons, nearly 3,000 times more powerful than our hypothetical scenario. But here is what it would be: a civilization-ending event. The widespread global collapse of critical infrastructure, agriculture, and societal order would take generations to recover from. Dr. Elisabetta Pierazzo, who spent her career modeling asteroid impacts at the Planetary Science Institute, once calculated that an object around 500 meters hitting land would cause regional devastation, with global climate consequences lasting years. That model, however, was based on a typical solar system asteroid, 3I Atlas, with its interstellar velocity exceeds every model she worked with. But what if it strikes the ocean instead? You might assume water would provide a cushion. That assumption would be dead wrong. An ocean impact, in many ways, is worse. When a 450-meter object moving at 31 kilometers per second hits water, it does not slow down gently. It punches straight through the ocean like it is barely there, instantly vaporizing millions of tons of water on contact. This creates an enormous temporary cavity in the ocean that immediately collapses inward, generating a mega tsunami. We are talking about waves 300 feet high, radiating outward at 500 miles per hour. Let's assume it hits the mid-Atlantic, right in the center. Within 1 hour, waves would be screaming toward coastlines on both sides of the ocean. The entire eastern seaboard of the United States, the Caribbean, and the whole western coast of Europe and Africa, they are all in the primary impact zone. Major global cities like New York, Miami, London, and Lagos would be instantly submerged under hundreds of feet of water before any meaningful evacuation could be organized. The human cost is unthinkable, as billions of people live in low-lying coastal zones. The death toll from a mid-Atlantic impact would dwarf anything in recorded history, and the ocean impact comes with a chilling bonus horror: water vapor. The impact instantly vaporizes millions of tons of seawater, injecting it high up into the stratosphere. In the short term, this water vapor acts as a powerful greenhouse gas, creating intensely chaotic weather patterns, generating massive storms and hurricanes in places they have never formed before. Then, as the massive debris cloud blocks the sun, that stratospheric water vapor condenses and falls back to Earth as snow, vast amounts of snow. You would be looking at blizzards across temperate zones in the middle of summer. If this event happened at a different time of year, the extreme climate whiplash alone would devastate global ecosystems. So, could we see it coming in time to do anything? That is the question that haunts planetary defense scientists. Remember, 3I Atlas was first spotted in October 2024, and its closest approach is December 2025. That provides roughly 14 months of warning. That sounds like a long time, but here is the brutal reality. If it were on a collision course, 14 months is nowhere near enough time to mount a meaningful defense using current technology. NASA's DART mission, the one that successfully deflected the smaller asteroid Dimorphos in 2022, took years of planning and required a relatively slow-moving target. DART impacted Dimorphos at 6.6 kilometers per second. 3I Atlas is moving nearly 5 times faster. The kinetic energy required to deflect it even slightly is staggering, and the required precision is far beyond anything we have ever attempted. Lindley Johnson, NASA's former planetary defense officer, stated the problem bluntly in a 2019 interview. He said, "If we discover an object with less than a year until impact, Our options range from very limited to none, and that statement was made regarding near-Earth asteroids that we have been tracking for decades. An interstellar intruder coming from a gravitational blind spot would leave us, to use the technical term, completely unprepared. But again, the science is clear. 3I Atlas is missing us. It is passing safely by 2.5 million miles. The orbital calculations are solid, and the trajectory is locked in. December 19th, 2025 will be a day of wonder, not terror. However, that hypothetical nightmare scenario we just walked through is not science fiction. It is a mathematical certainty that eventually something of this destructive power will be on a collision course with Earth. The question is not if it will happen, but when and whether humanity will be ready to meet the challenge. Which leads us directly to the uncomfortable truth about how we nearly missed 3I Atlas in the first place, and why our current detection systems still have gaps big enough for a city-sized object to slip through unnoticed. Here is the critical vulnerability that the approach of 3I Atlas has exposed. We were incredibly fortunate with this object because our planet-wide system for detecting incoming threats has a massive, glaring blind spot. And 3I Atlas approached Earth from exactly that direction. To understand why this happens, we must explain how humanity currently watches the sky for dangers. Right now, our primary asteroid detection network consists of a handful of ground-based telescopes scattered across the globe. The major players in this network are NASA's Atlas system, which operates 4 telescopes in Hawaii, Chile, and South Africa, the Catalina Sky Survey in Arizona, and Pan-STARRS, also located in Hawaii. These telescopes operate on a simple principle. They repeatedly photograph the same patches of the night sky, image after image. Then, automated software analyzes these sequences to detect anything that moves against the background of fixed stars. It is essentially a high-stakes, cosmic game of spot the difference. This method works brilliantly for objects that are already established in our solar system and are orbiting predictably around the sun at night. But there is a fundamental physical limitation. All of these telescopes are located on Earth. Obviously, Earth orbits the sun. This means that for roughly half of the sky, the half located in the direction of the sun, we are effectively blind. You cannot point a sensitive optical telescope at the sun and expect to see anything other than a fried camera sensor and a very expensive repair bill. There is a massive cone of space stretching from Earth toward the sun and beyond, where objects can approach completely undetected until they move into a position where sunlight is not overwhelming our instruments. 3I Atlas approached from almost exactly that vector. For weeks, it was hidden in the intense solar glare, invisible to all ground-based surveys. By the time it moved into a patch of sky dark enough to observe, it was already well inside the orbit of Mars. Dr. Larry Deneau, one of the lead scientists on the Atlas project, described the discovery as comparable to catching an intruder who has already broken into your house. We did not spot this thing approaching from deep space. We found it when it was practically on our doorstep. You might argue that the system eventually worked because we did spot it. That is true, but only because 3I Atlas was not on a collision course. If you want to understand the reality of this failure mode, consider the event of July 25th, 2019. On that day, an asteroid designated 2019 OK screamed past Earth at a distance of just 45,000 miles. That is about 1/5 of the distance to the Moon. That is closer than some of our geostationary satellites. The terrifying part is that we did not detect it until the day before it passed. We had 24 hours of warning for a 100-meter rock. If that rock had impacted a city, it would have released energy equivalent to 30 Hiroshima bombs. Why did we miss 2019? Okay, until the final moment. It was the exact same reason. It approached from the direction of the sun. Michael Brown, an associate professor at Monash University who analyzed the event, stated in an interview, "This one came out of a blind spot. We had no chance of seeing it until it was almost too late. The asteroid was traveling at 54,000 miles per hour, moving across the sky too fast for most survey telescopes to track properly, even when it became visible. By the time astronomers realized what was happening, it had already passed us. We literally watched our potential doom fly by in the rearview mirror." Here is another statistical reality that highlights the scale of the problem. NASA estimates there are roughly 25,000 near-Earth asteroids, larger than 140 meters, large enough to cause massive regional devastation. As of 2024, we have found and catalogued only about 40% of them. That means there are approximately 15,000 potentially city-killing rocks currently orbiting the Sun, and we have absolutely no idea where they are. Some of them are likely in orbits that bring them uncomfortably close to Earth every few years. We simply have not been looking in the right place at the right time to spot them yet. And that statistic only covers asteroids native to our solar system, objects that follow predictable elliptical paths and return on schedule like cosmic clockwork. Interstellar objects like 3I Atlas are an entirely different category of threat. We have no predictive capability for them whatsoever. They arrive from random directions at random times, moving at velocities that dwarf anything gravitationally bound to our Sun. Until one enters our solar system and gets close enough to reflect sunlight that our sensors can detect, it is completely invisible. We are talking about objects that could be spotted months before arrival at best, or weeks at worst. So, how do we solve this physics problem? The solution sounds simple. We must put telescopes in space where they are not limited by Earth's daylight cycle and can observe in all directions continuously, and we are actively working on this. NASA's NEO-Surveyor mission, short for Near-Earth Object Surveyor, is a space-based infrared telescope specifically designed to hunt asteroids. It is scheduled to launch around 2027. Its planned position is at a gravitationally stable point between Earth and the Sun, known as Lagrange Point 1. This position will allow it to look back and observe objects approaching from the sunward direction that ground telescopes physically cannot see. According to NASA's projections, NEO-Surveyor could catalog 90% of near-Earth asteroids larger than 140 meters within a decade of operation. But here is the catch. It has not launched yet, and it has been delayed multiple times due to budget constraints. The current projected cost is around $1.2 billion over the mission's lifetime. That sounds like a massive amount of money, until you realize that the United States military spends more than that on a single B-2 Spirit stealth bomber. We are talking about a system that could provide early warning of civilization-ending impacts, yet it has been chronically underfunded and delayed because, frankly, asteroid defense is not a politically urgent priority until a threat appears. Let us discuss detection speed, because that is the other critical factor often ignored. Even with perfect sky coverage, you need time to confirm that a spot of light is actually a threat. When a new object is detected, astronomers need multiple observations over several days or weeks to calculate its orbit accurately. This is not paranoia. This is mathematics. A tiny error in measuring an object's current position translates to a massive uncertainty in where it will be months later. You need enough distinct data points to plot a reliable trajectory, and gathering those points takes time. With 3I Atlas, Astronomers had the luxury of 14 months between detection and closest approach. That is an eternity in asteroid tracking terms. But remember, 2019, okay, we had 1 day of warning. Here is the nightmare scenario that keeps planetary defense experts awake. What if an interstellar object approached from the sun's direction on a collision course, and we only spotted it when it was 1 week out? What do you actually do with that information? The honest answer is, not much. You alert governments. You warn populations in the predicted impact zone to evacuate. You hope the calculations are wrong and it misses. But mounting any kind of physical defense in 1 week is impossible. Even getting a standard spacecraft off the ground takes months of preparation. You need to calculate complex intercept trajectories, fuel the rocket, run thousands of systems checks, and coordinate with international partners. 1 week might be enough time to evacuate a city, if you are lucky and people do not panic, but there is nowhere near enough time to stop the impact itself. This is why organizations like the Planetary Defense Coordination Office exist. Yes, that is a real office at NASA, established in 2016. Their entire job is to find, track, and characterize potentially hazardous asteroids, and to coordinate an international response if we ever face a real threat. But they will be the first to tell you that their capabilities depend entirely on early detection. Give them 5 years of warning, and they can potentially deflect an asteroid using kinetic impactors like the DART mission. Give them 5 months, and options start running out. Give them 5 weeks, and you are looking at emergency preparedness and damage control, not prevention. There is one more layer to this detection problem: false alarms. Every time we spot a new near-Earth object, there is a brief window where the uncertainty in its orbit is massive. Sometimes, an asteroid will initially appear to have a small statistical chance of hitting Earth, only for additional observations to rule out the impact entirely. This happens multiple times per year, and it has led to a kind of detection fatigue. News outlets report that an asteroid might hit Earth, then quietly update the story days later when better data shows it will miss. The public gets desensitized. So, when a real threat eventually appears, will anyone take it seriously? The scientific community has tools to handle this, such as NASA's Sentry system, which continuously monitors all known near-Earth objects and calculates impact probabilities. They use the Torino scale, which rates threats from 0 to 10 based on collision likelihood and potential damage. But these systems are only as good as the data feeding into them. If we miss the initial detection because an object came from a blind spot, none of those sophisticated risk analysis tools matter. So where does that leave us with 3i Atlas? We found it. We tracked it. We know it is not a threat. But the fact that an interstellar object could slip inside Mars's orbit before we spotted it should be a wake-up call. The gaps in our detection grid are not theoretical. They are real. They are exploitable. And eventually, something dangerous is going to come through one of them. But let's assume, purely for the sake of argument, that we actually possessed a perfect detection grid. Let's imagine we had 5 full years of warning before an interstellar object arrived on a collision course. Could we actually stop it? Or would we simply have 5 years to watch our inevitable doom approaching, powerless to change the outcome? This is where Hollywood has done the public a massive disservice. You have seen the movies. Bruce Willis drilling deep into an asteroid, nuclear bombs saving the day at the last second, heroes flying spacecraft directly into the heart of danger. It makes for compelling entertainment, but it has set up catastrophically wrong expectations about what we can physically achieve if a planet killer is heading our way. Let's start with the good news. We are not completely helpless. On September 26, 2022, humanity proved for the first time in history that we can physically alter the trajectory of a celestial body. NASA's DART spacecraft, the double asteroid redirection test, slammed into a small asteroid moon called Dimorphos at roughly 14,000 miles per hour. The impact was spectacular. Telescopes around the world watched as debris exploded outward from the collision site, and when scientists measured the orbit of Dimorphos afterward, they found something incredible. The asteroid's orbital period had changed by 33 minutes. DART had successfully nudged a rock off its path. Dr. Nancy Chabot, the DART coordination lead at Johns Hopkins Applied Physics Laboratory, called it humanity's first step in learning to defend ourselves from a cosmic impact. She is correct. It was a monumental achievement. But here is what the celebratory headlines did not emphasize. Dimorphos was the perfect target. It was relatively close, only about 7 million miles from Earth at the time of impact. It was moving slowly in cosmic terms, and critically, we were not trying to deflect it away from Earth to save the planet. We were merely testing whether we could change its orbit at all. The stakes were purely scientific, not existential. Now, let's apply that reality to 3I Atlas. Could we use a DART-style mission to stop it if we had to? The short answer is probably not. Here is why. DART worked because of a principle called momentum transfer. The spacecraft weighed about 1,200 pounds and was traveling at 6.6 kilometers per second when it hit. When you multiply mass times velocity, you get momentum. And when DART transferred its momentum to Dimorphos, the asteroid's velocity changed ever so slightly. But remember that word, slightly. We are talking about a velocity change measured in millimeters per second. For an asteroid that is already on a safe orbit, that tiny nudge is enough if you have years of lead time. A change of a few millimeters per second compounds into thousands of miles of deflection by the time the asteroid reaches Earth. It is like redirecting a train by moving the track just a few inches. When the train is still hundreds of miles away, by the time it reaches the station, it arrives at a completely different platform. However, 3I Atlas is moving at 31 kilometers per second. That is nearly 5 times faster than Dimorphos was moving relative to DART, and it is significantly larger. Remember, we estimated 3I Atlas to be 450 meters in diameter, compared to Dimorphos's 160 meters. Bigger size means significantly more mass. More mass means more momentum, and the faster something is moving, the harder it is to change its trajectory. You would need an exponentially bigger impact to achieve the same deflection. How much bigger? Let's do some rough math. If you wanted to deflect 3I Atlas by enough to make it miss Earth, and you only had 1 year of warning, you would need to change its velocity by several meters per second, not millimeters. That is thousands of times more momentum transfer than DART achieved. You would need to hit it with something massive, moving incredibly fast, or both, which brings us to the option nobody wants to discuss publicly, but everyone in the defense community is thinking about: nuclear weapons. Before you roll your eyes at the Hollywood cliché, hear me out, because the real science of nuclear deflection is both more interesting and more sobering than the movies show. Contrary to what the movie Armageddon taught a generation of viewers, you do not drill into an asteroid and blow it up from the inside. That is absurd physics. What you actually do is detonate a nuclear device near the object, not on it, but near it, and use the intense X-ray energy from the explosion to instantly vaporize a thin layer of the asteroid's surface. That vaporized material jets away from the asteroid at high speed, and Newton's third law kicks in. For every action, there is an equal and opposite reaction. The jetting material acts like a massive rocket engine, pushing the asteroid in the opposite direction. This is not science fiction. It is a real concept called nuclear deflection, and scientists have been studying it for decades. A 2007 NASA study titled Near-Earth Object Survey and Deflection Analysis of Alternatives examined nuclear deflection as a primary option. The conclusion was clear. For large asteroids with short warning times, nuclear deflection is actually the most effective method we currently possess. A single 1 megaton nuclear device detonated at the correct standoff distance could impart enough energy to deflect a large asteroid significantly. But, and this is a massive but, it requires incredible precision. Detonate too close, and you might fracture the asteroid into multiple large pieces that are still on a collision course. Now, instead of one impact, you have a shotgun blast of a dozen impacts. Detonate too far away, and the energy dissipates into the vacuum of space without doing anything useful. You need to know the asteroid's exact composition, rotation rate, and structural integrity. You need to calculate the precise distance and orientation for the detonation, and you need to deliver the warhead to that exact spot, millions of miles away, at exactly the right second. Oh, and there is one more significant problem: international law. The Outer Space Treaty of 1967, which has been signed by over 110 countries, including the United States and Russia, explicitly bans the placement of nuclear weapons in space. While there might be a provision for exceptions in extraordinary circumstances, can you imagine the political negotiations required to get international consensus on launching high-yield nukes into space? While a planet killer is bearing down on us, the bureaucracy alone might doom us. Let's assume we somehow cleared all those political hurdles. We built a nuclear deflection mission, launched it, and successfully intercepted 3I Atlas. Here is the next problem. Interstellar objects are fundamentally different from near-Earth asteroids. We know almost nothing about their internal composition. Is 3I Atlas a solid rock monolith? Is it a rubble pile, basically a bunch of smaller rocks held together loosely by gravity? Or is it a comet with a fragile, icy structure? The deflection strategy changes dramatically depending on the answer. If it is a rubble pile, then any impact, nuclear or kinetic, might just scatter it without changing its overall trajectory, center of mass. The pieces would continue along roughly the same path, and you would have turned one big problem into 100 smaller problems. If it is a solid monolith, great. Momentum transfer works efficiently. But if it is a comet with a thick ice layer, the nuclear heat might cause catastrophic, uneven outgassing that pushes it in unpredictable directions. And here is the timeline issue. The DART mission took nearly 10 years from initial concept to launch. 10 years of planning, engineering, testing, and preparation to hit a target we had been studying for years beforehand. With 3I Atlas, we would have had 14 months from detection to impact. In our hypothetical scenario, you cannot design, build, test, and launch a complex planetary defense mission in 14 months. It is physically impossible with current technology and industrial infrastructure. So, what about other options? There is the gravity tractor concept, sending a heavy spacecraft to fly alongside the asteroid and using the tiny gravitational pull between them to slowly tug it off course. It is elegant, it is fully controllable, and it requires absolutely zero explosive impact. The problem? It is mind-numbingly slow. You would need years, maybe decades, of continuous operation to build up enough deflection. This is great for an asteroid we spot 50 years before impact. It is useless for something 14 months out. There is laser ablation, using powerful lasers to vaporize surface material and create thrust through the same rocket engine principle as nuclear deflection, just gentler and more precise. NASA has been studying this. The engineering challenges are immense, but it is theoretically possible. Again, though, it is a long-term solution. You would need sustained laser fire over months or years. Some researchers have proposed using multiple kinetic impactors, not just one DART-style spacecraft, but a whole fleet of them slamming into the asteroid in sequence. Each one adds a little more deflection. This could theoretically work for 3I Atlas, but building and launching multiple spacecraft on short notice brings us back to the timeline problem. Here is what it comes down to. Planetary defense is like car insurance. It only works if you have it before you need it. With asteroids native to our solar system, we can track them decades in advance, giving us time to mount a measured response. But interstellar objects like 3I Atlas are the equivalent of a drunk driver running a red light at 100 miles per hour. By the time you see them, your window to react is almost closed. Tom Statler, NASA's DART program scientist, said something in a post-impact interview that stuck with me. He said, "DART proved we can move an asteroid. What it didn't prove is that we can do it fast enough when it really matters. And that is the uncomfortable truth. We have taken the first step in defending Earth, but we are nowhere near ready for a real crisis, especially one involving an object from interstellar space." So, if we cannot reliably stop 3I Atlas in our hypothetical nightmare scenario, what precisely could we do with 14 months of warning? The answer is both practical and deeply unsettling. And it starts with understanding exactly what this interstellar visitor is made of, which leads us directly into some truly bizarre physics. Understanding the composition of 3I Atlas is not just a matter of academic curiosity. It is the fundamental difference between predicting its behavior accurately and being completely blindsided by a phenomenon we never saw coming. And right now, this object is doing things that make scientists deeply uncomfortable. Let's start with what we can actually observe. When astronomers point telescopes at 3I Atlas, they are not simply taking high-resolution photographs. They are performing spectroscopy. This process essentially breaks down the light reflecting off the object into its component wavelengths, much like a prism splitting white light into a rainbow. Different chemical elements and compounds absorb and reflect light at very specific, predictable wavelengths, creating a unique signature. It is effectively CSI for space rocks, and the chemical fingerprint of 3I Atlas is telling us a strange story. The spectroscopic data shows clear, unmistakable signatures of water vapor, carbon dioxide, and carbon monoxide outgassing as the object heats up while approaching the sun. On the surface, this is classic comet behavior. Comets are often described as dirty snowballs, large chunks of ice mixed with rock and dust that begin to vaporize when solar radiation warms them up. So far, this appears normal. But here is where the data gets weird. The ratio of these gases does not match any comet we have ever studied in our own solar system. Dr. Alan Fitzsimmons from Queen's University Belfast, who studied the previous interstellar visitor 2I Borisov extensively, noted that interstellar comets can have chemical compositions wildly different from local ones because they formed around different stars under completely different conditions. With 2I Borisov, scientists found carbon monoxide concentrations anywhere from 9 to 26 times higher than typical solar system comets. That was our first concrete hint that objects from other star systems might be fundamentally different at a chemical level. But 3I Atlas is showing something even stranger. The measurable amount of gas it is releasing does not correlate properly with its observed brightness changes. Normally, when a comet outgasses, the escaping gas and dust create a visible coma, a fuzzy cloud around the nucleus, and the object's brightness increases predictably based on how much material is being released. With 3I Atlas, the brightness is fluctuating in ways that suggest the surface is not uniform. Parts of it might be covered in highly reflective, fresh ice, while other areas could be covered in dark, rocky material. As it rotates, different faces point toward the sun, and we are seeing wildly different levels of activity. This rotation brings up another puzzle. Based on the brightness variations, astronomers estimate that 3I Atlas completes one full rotation roughly every 8 to 12 hours. They are still refining the exact period, but that is actually quite fast for an object of this size. Here is why that speed matters. If this object is a loose rubble pile rather than a solid chunk, spinning that fast could generate enough centrifugal force to cause it to fly apart. The fact that it is staying intact tells us it either has significant internal structural strength, or it is held together by forces we do not fully understand yet. Think about Oumuamua for a second. Remember how the scientific community reacted to its unexplained acceleration? Scientists proposed dozens of explanations. Maybe it was outgassing hydrogen, which would be invisible to our optical telescopes. Maybe it was tumbling in such a complex way that outgassing jets pushed it in unexpected lateral directions. Or maybe, and this is where the theories became extreme, it was an artificial object. Harvard physicist Avi Loeb seriously suggested it could be a light sail from an alien civilization, using radiation pressure from the sun for propulsion. The scientific community largely rejected the alien hypothesis due to a lack of evidence. But here is the critical point. We still do not have a completely satisfying, unified natural explanation for Oumuamua's behavior. And now 3I Atlas is showing similar anomalies. That 15% extra acceleration we cannot account for is hauntingly familiar. One explanation gaining serious traction involves supervolatiles chemicals that vaporize at extremely low temperatures. Regular comets outgas water and carbon dioxide when they get relatively close to the sun. But what if interstellar comets also contain significant amounts of molecular nitrogen or carbon monoxide ice? These materials start vaporizing much farther from the sun, in the cold depths of space where we can barely detect the activity. The outgassing would be invisible or nearly invisible to our current instruments, but the rocket effect would still push the object along. A 2020 study published in Nature Astronomy by researchers at Yale University examined this exact hypothesis for Oumuamua. They calculated that if the object was composed of 90% nitrogen ice, similar to the surface of Pluto's moon, Triton the outgassing could explain the acceleration without producing visible jets. It is a compelling theory, but here is the catch. Nitrogen ice sublimates, turns from solid to gas, extremely rapidly when exposed to direct sunlight. If Oumuamua was made of pure nitrogen, it should have lost a significant fraction of its mass during its trip through our solar system, and yet, observations did not show the dramatic brightness changes you would expect from an object actively evaporating at that rate. So, what does this mean for 3I Atlas? If it is following a similar pattern, we might be seeing only part of the physical picture. The visible outgassing of water and carbon dioxide could be happening on sun-facing surfaces, while invisible, super-volatile outgassing occurs elsewhere, creating thrust we can measure but not see. It is like watching a boat move across a lake and seeing the wake on one side, while there is an underwater propeller you cannot see spinning on the other side. You are trying to calculate the boat's total speed with incomplete information. Here is another fascinating angle: the journey itself. 3I Atlas has been traveling through interstellar space for potentially millions of years. What does that exposure do to an object? Interstellar space is not empty. It is filled with cosmic rays, high-energy particles that bombard anything passing through. Over geological timescales, this radiation can fundamentally alter the chemistry of surface materials. Ice can be chemically converted into more complex organic molecules. Rocks can have their crystal structures rearranged. By the time an interstellar object reaches us, its outer layers might be completely different from its interior. Some researchers call this the cosmic weathering effect. There is a hypothesis that Oumuamua might have been covered in an organic-rich crust created by millions of years of radiation exposure, essentially a protective coating built up during its journey. When it got close to the sun, this crust could have started vaporizing or fracturing in ways that do not match our models for fresh comets. If 3I Atlas possesses similar weathering, it would explain why its behavior does not match our models for objects native to our solar system. But here is what really frustrates astronomers making all these observations from millions of miles away. We are never going to get a close-up look. We are never going to land a probe on it or return a sample to a lab. By the time we have finished analyzing the data from December 19th, 3I Atlas will already be racing back out into interstellar space, never to return. Everything we learn must come from telescopic observations made during its brief pass through our neighborhood. And those observations are strictly limited by physics. Even the James Webb Space Telescope, the most powerful observatory ever built, can only resolve details down to a certain size at this distance. We can see the overall shape probably elongated, like most comets, but we cannot map surface features like craters or ridges. We can measure the total amount of gas being released, but we cannot pinpoint exactly which regions are active. We are effectively like doctors trying to diagnose a patient through a frosted glass window from across the room. There is one more layer to this mystery. Where did the material that makes up 3I Atlas originally come from? Not which star system, but which part of that star system. In our own solar system, we know that objects formed at different distances from the Sun have drastically different compositions. Mercury is mostly metal and rock. Earth has water and organic compounds. The outer planets are gas and ice giants. Kuiper Belt objects, way out past Neptune, are rich in frozen volatiles. If 3I Atlas was formed in the outer reaches of its home system, the equivalent of our Kuiper Belt, it would be icier and volatile heavy. If it formed closer in, it might be rockier, with less ice. The chemistry we are observing suggests 3I Atlas formed in the cold outer regions of another star system, then got gravitationally ejected during some chaotic event, probably planetary migration or a close encounter with a giant planet. It has been wandering the galaxy ever since, slowly accumulating that cosmic weathering crust, until gravity from our sun bent its path inward for this brief, spectacular visit. But all the spectroscopy and orbital mechanics in the world cannot answer the question most people actually want to know. What is it going to look like when it passes by Earth? Will you be able to see it with your own eyes? Or do you need a professional observatory? And more importantly, what are scientists actually going to do during those precious hours when 3I Atlas is at its closest? Let's get real about December 19th. But what is it actually going to look like from your own backyard? Can you simply walk outside on December 19th, look up at the night sky, and witness an interstellar visitor screaming past Earth with your own eyes? The answer is likely going to disappoint a lot of people. Probably not with your naked eyes. Here is the reality. Based on current brightness predictions, 3I Atlas will likely reach a visual magnitude somewhere between 10 and 12 at its closest approach. If you are not familiar with the magnitude scale astronomers use, it works backward. Lower numbers mean brighter objects. For context, the faintest stars you can see with your naked eye on a perfectly dark, moonless night are around magnitude 6. The planet Venus, blazing bright in the evening sky, sits around magnitude -4. So, magnitude 10 to 12 is firmly in telescope territory. It is hundreds of times fainter than what the human eye can detect. To see it, you will need at least a decent backyard telescope, something with a 6-inch mirror or larger, and you will need access to dark skies away from city light pollution. But here is where it gets genuinely interesting for amateur astronomers. Unlike stars, which appear as fixed points of light, 3I Atlas will be moving fast, really fast. If you are tracking it through a telescope eyepiece, you will actually see it drift noticeably across your field of view over the course of just a few minutes. That is a rare experience. Planets move against the background stars, sure, but they do so over days and weeks, not in real-time viewing sessions. Watching 3I Atlas will be like spotting a very distant, slow-moving airplane through your telescope, except this airplane is a half-kilometer chunk of ice and rock from another star system traveling at 7,000 miles per hour. The best viewing locations are going to be in the southern hemisphere during the closest approach. Think Chile, Australia, South Africa, and New Zealand. Northern observers aren't completely out of luck, but the orbital geometry isn't in your favor. For us in the north, the object will be lower on the horizon, meaning you are looking through a thicker layer of Earth's atmosphere, which blurs and dims the image. Professional observatories on high mountains in Hawaii and the Canary Islands will have decent shots, but the prime viewing real estate is definitely south of the equator. Now, even if you cannot see it yourself, you will absolutely be able to watch it live. NASA has already announced plans to stream observations from multiple professional telescopes during the December 19th flyby. The European Southern Observatory's Very Large Telescope in Chile, and yes, that is its actual name, will be tracking it continuously. So will the massive Subaru telescope in Hawaii and the Gemini Observatory. These facilities have cameras sensitive enough to capture objects 1,000 times fainter than what even the best amateur telescopes can see, and they will be feeding real-time data and images to astronomers worldwide. But the real scientific show is happening in wavelengths of light you cannot see with any optical telescope. This is where the space-based heavy hitters come in. The James Webb Space Telescope will be observing 3I Atlas in infrared. Infrared is essentially heat. This allows scientists to map temperature variations across the object's surface, which reveals crucial information about its composition and structure. Is one side significantly icier than the other? Are the jets of gas erupting from specific, localized regions or from the entire surface? Infrared data can answer those questions. The Hubble Space Telescope is also getting time booked for observations. Hubble might be old compared to James Webb, but it is still phenomenally capable in visible and ultraviolet wavelengths. Ultraviolet light is particularly useful for detecting certain gases that do not show up clearly in visible light. When water vapor and other molecules break apart in sunlight, they fluoresce or glow in UV light. Hubble can map that fluorescence and tell scientists exactly which parts of the comet are actively outgassing. Here is something most people do not realize. Observing time on these space telescopes is absurdly competitive. Astronomers submit detailed proposals months or years in advance, and committees evaluate hundreds of applications for every single hour of telescope time available. The fact that 3i Atlas has secured priority time on James Webb, Hubble, and multiple ground-based observatories tells you exactly how significant this event is to the scientific community. They are treating this like the astronomical equivalent of a royal wedding. Everyone wants a piece of the action. So, what exactly are they hoping to learn? The observation campaign has several specific, critical goals. First, nailing down the exact size and shape. Right now, estimates range from 300 to 600 meters, which is a huge margin of uncertainty. High-resolution imaging during the closest approach should narrow that down significantly. Second, measuring the rotation period precisely. This tells us about the object's internal structure, whether it is a solid chunk of rock or a loosely bound rubble pile, held together by weak gravity. Third, and perhaps most importantly, cataloging every chemical species outgassing from the surface. This is the big one. Every molecule detected is a clue about the conditions in the star system where this object formed. There is also a specific search happening for organic molecules, carbon-based compounds that are the fundamental building blocks of life. Now, before anyone gets excited about aliens, let me be clear. Finding organics on a comet does not mean finding life. Organic molecules form naturally in space all the time through basic chemistry, but finding them here would tell us something profound about the raw ingredients available in other star systems. If 3i Atlas is loaded with complex organics, it suggests the star system it came from had a chemical inventory similar to what led to life on Earth. Dr. Martin Cordiner, an astrochemist at NASA's Goddard Space Flight Center who led a study on 2I Borisov's composition, said something that defines this entire mission. He called every interstellar object a sample return mission we didn't have to pay for. Think about that. We spend billions of dollars sending spacecraft to asteroids and comets in our own solar system to bring back tiny amounts of material. But interstellar objects deliver themselves to our doorstep, carrying physical evidence of entirely different star systems. We cannot touch them, but we can study them in ways that are impossible for objects light years away. And there is a citizen science angle here that is genuinely exciting. Amateur astronomers with mid-sized telescopes can contribute real scientific data. Organizations like the American Association of Variable Star Observers are coordinating massive global observation campaigns. If you have a telescope, a decent digital camera, and clear skies, you can submit your observations to a central database. Professional astronomers actually rely on this data to fill in gaps in coverage. Remember, even the biggest observatories cannot watch something 24/7. When Hubble needs to slew to a different target, or when clouds roll over the mountains in Chile, the professional feed goes dark. Amateur astronomers in different time zones can keep the observation chain going. Here is a practical example of why that matters. When Oumuamua passed through in 2017, there were only a handful of days when it was bright enough for detailed study. Scientists had to frantically coordinate observations across multiple telescopes to get enough data. And even then, there were frustrating gaps in coverage that left key questions unanswered. With 3i Atlas, the astronomy community is determined not to make the same mistake. The plan is continuous, unbroken coverage from detection through closest approach and beyond, tracking this thing for as long as physically possible before it fades from view. One of the most ambitious observation goals is measuring the object's mass. You cannot just put a comet on a scale. So, how do you figure out how heavy it is? The trick involves watching how it responds to gravitational interactions. As 3I Atlas passes relatively close to Earth, remember, 2.5 million miles our planet's gravity will very slightly alter its trajectory. By measuring the exact change in velocity and direction, scientists can back-calculate the object's mass. It is like watching a billiard ball deflect off another ball and using the angle of deflection to figure out how heavy each ball is. Why does mass matter? Because density equals mass divided by volume. If you know the size and the mass, you can calculate average density, and density tells you composition. If 3I Atlas has a density around 0.5 grams per cubic centimeter, it is probably a fluffy ice and dust mixture. If it is closer to 2 or 3 grams per cubic centimeter, there is significant rocky or metallic material in there. Suddenly, you know whether this thing is a pristine comet or something rockier that has been heavily processed. There are also going to be radar observations, which are fascinating because radar is one of the few ways to probe beneath the surface. The Arecibo Observatory in Puerto Rico used to be the gold standard for asteroid radar before its tragic collapse in 2020. But the Goldstone Deep Space Communications Complex in California is still operational and highly capable. Radar works by bouncing powerful radio waves off the object and analyzing the echo. The time delay tells you the distance with incredible precision. The way the radio waves scatter back tells you about surface texture. Smooth ice reflects differently than rough rock. But here is the limitation. Radar range drops off extremely fast. For Goldstone to get usable data, 3I Atlas would need to be within a few million miles, which it will be, but only briefly. The window for radar observation is measured in hours, not days. That is why coordination is critical. Every observatory, every amateur astronomer, and every piece of specialized equipment needs to be perfectly timed to maximize data collection during the flyby. And when it is all over, when 3I Atlas has whipped past Earth and is accelerating back toward the outer solar system, scientists will have terabytes of data to sift through. Doctoral theses will be written about this single object for decades. We will learn things about planetary formation, stellar system evolution, and the nature of interstellar space that we simply cannot learn any other way. But beyond the pure science, there is something profoundly deeper happening here. On December 19th, humans around the world will be watching an object that originated from another star. It is a piece of cosmic real estate that was never ours, passing through on a journey that started in a place we will likely never visit. It serves as a stark reminder of just how unimaginably vast the universe is, and how small our corner of it really is. This realization raises an unsettling question. If interstellar objects like 3I Atlas are passing through regularly, what else is out there that we simply have not noticed yet? The uncomfortable truth is that 3I Atlas is probably not alone. In fact, statistically speaking, it is almost certainly not alone. Right now, as you are listening to this, there are likely dozens, perhaps even hundreds of interstellar objects passing through our solar system completely undetected. And the math behind that statement is both fascinating and deeply unsettling. Let's start with what we know for a fact. In the span of just 8 years, between 2017 and 2025, humanity has confirmed 3 interstellar objects: Oumuamua, 2I Borisov, and now 3I Atlas. 3 confirmed visitors in 8 years. But here is the critical context. Our detection capabilities are laughably incomplete. We are only catching the objects that happen to pass relatively close to Earth, are large enough to reflect detectable sunlight, and are located in a specific part of the sky we happen to be surveying at that exact moment. It is like standing in a vast, dark forest with a narrow flashlight beam and assuming you have seen all the animals just because you spotted 3 deer crossing the path. In 2019, a team of researchers at Harvard, led by Amir Siraj, published a paper in the astrophysical journal Letters that attempted to estimate how many interstellar objects actually pass through the inner solar system at any given moment. Their calculations, based on the detection rates of Oumuamua and Tuai-Borisov, suggest that at any given time, there could be roughly 100 interstellar objects closer to the Sun than Neptune. 100 objects, and we have found 3. Think about that ratio for a second. We are detecting roughly 0.03% of what is actually out there. It is the statistical equivalent of knowing your house has a mouse problem because you saw one run across the kitchen floor, but you do not realize there are thousands living inside the walls. The size distribution makes this even more wild. Most of the interstellar objects passing through are likely small, measured in meters, not hundreds of meters like 3I Atlas. Objects of that size are nearly impossible to detect with current technology unless they pass extremely close to Earth. But the researchers' models suggest that objects in the 100-meter range or larger pass through the inner solar system multiple times per year, every single year. We are just not seeing them because our surveys aren't sensitive enough, or they are approaching from blind spots like the sunward direction, or they are moving too fast for our tracking software to flag them as interesting before they have already left the system. Here is where it gets even stranger. Some scientists believe there might be interstellar objects that do not just pass through, they get captured. Imagine an interstellar wanderer approaching our solar system and having a close gravitational encounter with Jupiter or Saturn under very specific mathematical conditions. That encounter could rob the object of enough velocity to trap it in a permanent orbit around the Sun. It would no longer be on a hyperbolic escape trajectory. It would become a permanent resident, effectively indistinguishable from native solar system objects, except for its highly unusual orbit. Dr. Fathi Namouni from the Côte d'Azur Observatory in France has studied this exact scenario. In 2018, he and his colleague Maria Helena Moraes published research suggesting that certain asteroids with weird retrograde orbits, meaning they orbit the Sun in the opposite direction from the planets, might actually be captured interstellar objects. One prime candidate is an asteroid designated 2015 BZ 509, which shares an orbit with Jupiter but goes around the Sun backward. The orbital dynamics suggest it likely did not form here. It is an immigrant, gravitationally trapped millions of years ago. How many other asteroids in our massive catalog are actually interstellar refugees? We simply do not know. We have cataloged over 1 million asteroids, but detailed orbital analysis to check for interstellar origins has been done on only a tiny fraction. There could be hundreds or thousands of former wanderers hiding in plain sight, and we would never know unless we specifically looked for the telltale signs of capture dynamics. Now, let's zoom out even further to the galactic scale. The Milky Way galaxy is massive, containing over 100 billion stars. Based on what we have learned from exoplanet surveys like Kepler, most of those stars have planetary systems, and during the chaotic formation of every single one of those planetary systems, gravitational interactions ejected countless objects into interstellar space. We know this happened in our own solar system. The Kuiper Belt and Oort cloud are full of icy bodies, but models suggest billions more were thrown out entirely during the early days when Jupiter and Saturn were migrating to their current orbits. Multiply that process across 100 billion star systems, and you get a staggering number. Estimates suggest there are roughly 10 to the 26th power interstellar objects wandering the Milky Way. That is 100 trillion objects. The space between stars is not an empty void. It is an ocean of debris, frozen leftovers from planetary formations scattered across the galaxy. Most of those objects are small, comet-sized, asteroid-sized, or boulder-sized, but statistically, some of them have to be huge. We are talking about rogue planets, entire worlds ejected from their home systems, and now drifting alone through the darkness. In 2011, a team of researchers using gravitational microlensing data estimated there could be twice as many rogue planets as there are stars in the galaxy. Think about that. Twice as many rogue planets as stars. Entire worlds, potentially with moons, atmospheres, and maybe even subsurface oceans, wandering between the stars with no sun to orbit. Could one of those rogue planets pass through our solar system? The odds are vanishingly small, but they are not zero. If it happened, the gravitational disruption would be catastrophic. A Jupiter-mass rogue world passing through the inner solar system would wreak havoc on planetary orbits. Earth could be flung into a different orbit, closer to the sun or farther away. Either scenario would end life as we know it. The good news is that space is so incomprehensibly vast that the chances of a close encounter with something that massive are almost negligible on human timescales. Almost. But smaller objects? Those are a real and present concern. Every year, Earth is hit by meteors, small chunks of rock and ice burning up in the atmosphere. Most are millimeter to centimeter in size. But statistically, some percentage of those meteors are probably interstellar. They are moving too fast and coming from weird angles, but they burn up before anyone can study them properly. We have likely been pelted by interstellar debris for billions of years without realizing it. In 2014, something very interesting showed up in the government sensor data. Researchers analyzing meteor observations detected an object that entered Earth's atmosphere over Papua New Guinea. It was moving at roughly 60 kilometers per second, far faster than anything gravitationally bound to the sun should be moving. It exploded in the atmosphere, but the velocity vector strongly suggested an interstellar origin. If confirmed, it would have been the first detected interstellar object, predating Oumuamua by 3 years. But meteor data is often noisy, and the observation wasn't conclusive enough for official confirmation at the time. Still, it raises the question, how many interstellar meteors have hit Earth, and we just didn't notice because they weren't big enough or fast enough to stand out? There is also the question of directionality. Are interstellar objects coming from random directions, or is there a pattern? Some researchers have suggested that if the solar system is currently passing through a denser region of the galaxy, maybe the remnants of a star cluster that dispersed long ago, we could be encountering more interstellar debris than the galactic average. It is like driving through a swarm of bugs on the highway. Most of the time you are in open air, but occasionally you hit a dense cloud and your windshield gets plastered. The local bubble, a region of low-density, hot gas about 1,000 light-years across that our solar system is currently inside, was probably created by supernova explosions millions of years ago. Those explosions would have scattered debris across a huge volume of space. Some of that debris could still be drifting around, and we might be encountering it right now. Now, what is particularly unnerving is the detection lag. Remember, we only spotted 3I Atlas in October 2024, and it is passing Earth in December 2025. That gave us roughly 14 months of warning. Now, imagine an object on a similar trajectory, but slightly smaller, maybe 200 meters instead of 450. It would be significantly fainter and harder to detect. We might not spot it until it was only a few months out, or even weeks. What do you actually do with information like that? Here is the scenario that keeps planetary defense experts awake at night. An interstellar object, perhaps 150 meters across, approaching from the sun's direction, is detected just 3 weeks before closest approach. Initial orbit calculations show a 5% chance of impact. Not certain, but absolutely not negligible. You cannot evacuate entire continents on a 5% probability. You cannot launch a deflection mission in 3 weeks. All you can do is frantically refine the calculations and hope the uncertainty resolves in your favor. That is not science fiction. That is an entirely plausible scenario given our current detection capabilities and the estimated frequency of these interstellar visitors. And the situation gets significantly worse when you consider velocity. Our current planetary defense strategies, what little we actually have, are built entirely around near-Earth asteroids that typically move at speeds between 10 and 25 kilometers per second relative to Earth. Interstellar objects play by a different set of rules. They can come screaming in at 30, 40, or even 50 kilometers per second. In orbital mechanics, speed is the enemy of response time. The faster an object is moving, the less time you have to react, the harder it is to track accurately, and the exponentially harder it is to deflect. The galaxy is effectively sending us packages we didn't order, and most of them are arriving without tracking numbers or return addresses. 3I Atlas happens to be one we caught early enough to study. But statistically, there are others out there right now, some of them potentially much closer than this one, and we have absolutely no idea they exist. Which brings us to an uncomfortable but necessary question. What are the actual odds? What is the real probability that something catastrophic is heading our way right now? And how do those odds compare to the other existential risks humanity faces? Let's talk numbers. Real, hard numbers. Because when it comes to asteroid impacts, there is often a lot of fear-mongering and not nearly enough actual risk assessment. NASA's Near-Earth Object Program has been cataloging potential threats for decades, and they've developed a sophisticated tool called the Palermo Technical Impact Hazard Scale. Unlike the simpler Torino scale, which is for public communication, the Palermo scale is a logarithmic mathematical tool used by specialists. It combines the probability of impact, the time until impact, and the kinetic energy of the object into a single risk value. Here is how it works. A Palermo scale value of 0 means the threat is roughly equal to the background risk, the average risk posed by other objects of similar size over the years. Anything above 0 means the threat is higher than the background level and warrants serious concern. Anything below -2 is generally considered statistically insignificant. As of late 2024, there are exactly 0 known objects with a Palermo scale value above 0 threatening Earth in the next century. That sounds reassuring, and it is. But let's put this in context. The asteroid that wiped out the dinosaurs, the Chicxulub impactor we discussed earlier, was a once-in-100 million years event. Geological evidence from impact craters tells us that objects of that size, roughly 10 kilometers in diameter, hit Earth, on average, every 100 to 200 million years. The last one was 66 million years ago. So statistically, we are not due for another extinction-level event anytime soon. However, Smaller impacts happen much more frequently. The Tunguska event in 1908, where an asteroid estimated at 50 to 60 meters across exploded over Siberia and flattened 2,000 square kilometers of forest, represents a class of impact that occurs roughly every 300 to 500 years. The Chelyabinsk meteor in 2013, a rock about 20 meters across that injured over 1,000 people, happens on average once every 60 years. And tiny meteors that burn up harmlessly in the atmosphere, those arrive by the thousands every single day. Here is the important part. We have gotten very good at tracking the big ones. NASA estimates we have found over 95% of near-Earth asteroids, larger than 1 kilometer. These are the civilization-threatening rocks. The few we haven't found yet are almost certainly in highly inclined orbits that do not bring them near Earth, or we likely would have spotted them by now. So, the existential level threat from native solar system asteroids is actually quite low, but interstellar objects change the entire calculation. Those comforting odds I just gave you are based on objects in predictable, elliptical orbits that we can track over decades. Interstellar visitors are random encounters. They are not part of the standard statistical model because we do not know how many there are or how often they pass through the inner solar system on trajectories that could threaten Earth. Let's try to estimate this anyway, based on the detection rates of Oumuamua, 2I Borisov, and 3I Atlas. Accounting for our limited detection capabilities, researchers estimate that an interstellar object larger than 100 meters passes within Earth's orbit roughly once per year. Most of those passages do not come anywhere near Earth itself. Space is big, and Earth is a tiny target. But statistically, over a long enough timeline, one of them will be on a collision course. How long is that timeline? Extremely rough estimates, and these come with massive error bars, suggest an interstellar impact large enough to cause regional devastation might occur once every 10 million to 100 million years. That sounds like similar odds to a Chicxulub-sized native asteroid. But here is the critical difference. Warning time. We can predict native asteroids decades in advance. With interstellar objects, we get months at best, possibly weeks. Dr. Gregory Laughlin from Yale University, who has done extensive modeling on interstellar object encounters, summarized the problem perfectly in a 2020 interview. He said, "The probability of an interstellar impact in any given year is vanishingly small, but the probability that we would have adequate warning if it happened is also vanishingly small. It is a double-edged sword, low probability, but catastrophic consequences combined with near zero preparation time. So, how does this stack up against other existential risks? When we compare them, we see distinct categories of threat. Climate change is happening right now, with measurable effects playing out over a timescale of decades, while the COVID-19 pandemic proved that biological threats are real, present, and carry immediate global consequences. Nuclear war remains a terrifying possibility, though hopefully one of low probability. Yet it is entirely within human control to prevent or cause. Similarly, the risks posed by artificial intelligence are hotly debated with a timeline that remains uncertain. And then there is asteroid impact, which stands apart as a unique category defined by low probability, extremely high consequence, limited warning, and at least for now, minimal control. Here is what makes asteroid defense unique among all existential risks. It is the only one that is entirely external to humanity, and yet entirely preventable with sufficient technology. We cannot negotiate with an asteroid. We cannot change its mind or appeal to its better nature. but we can detect it, track it, and potentially deflect it if we invest in the right systems. Which brings us to funding. NASA's Planetary Defense Coordination Office has an annual budget of roughly $150 million. That might sound like a lot of money until you realize it is less than 0.5% of NASA's total budget, and NASA's total budget is less than 0.5% of the total United States federal budget. We are spending about 50 cents per American per year on planetary defense. Compare that to the nearly $800 billion spent annually on military defense. The priorities are interesting, to say the least. And here is the kicker. The return on investment for planetary defense is theoretically infinite. If you successfully deflect a civilization-ending asteroid, you have saved literally everyone. Every person, every economy, every future generation. The cost-benefit analysis is absurdly positive. Even if the probability of impact is 1 in a million in any given year, the expected value of prevention is astronomical when you factor in the 8 billion lives at stake. But humans are notoriously bad at evaluating low probability, high consequence risks. We worry about shark attacks, which kill fewer than 10 people per year globally, while ignoring asteroid threats that could kill billions. It is a cognitive bias called probability neglect. Our brains did not evolve to think statistically about existential risks, because for 99.9% of human history, those risks did not exist in forms we could predict or prevent. Here is something that should shift your perspective. We are the first generation in the 4 billion year history of life on Earth that possesses the capability to prevent its own extinction from an asteroid impact. Think about that. Every mass extinction before us was inevitable. The dinosaurs could not build space telescopes or kinetic impactors. They went extinct because a rock from space hit them, and there was absolutely nothing they could do about it. But we can. We have the technology, or we are very close to having it, to detect threats and respond. The DART mission proved we can change an asteroid's trajectory. The NEO Surveyor telescope, if it launches as planned, will close the detection gaps that let objects like 2019 OK sneak up on us. We are on the cusp of making planetary defense a solved problem. Except we are not investing in it like it is a solved problem. We are treating it like a background risk that is someone else's responsibility. And that is dangerous, because the universe does not care about our budget priorities or political cycles. Let me give you a concrete scenario. Imagine it is the year 2035. An interstellar object is detected approaching from the sun's direction. Initial observations suggest it is 200 meters across, moving at 35 kilometers per second, and initial calculations show a 10% chance it hits Earth in 8 months. What happens next? In the current system, NASA alerts the International Asteroid Warning Network, a coalition of observatories worldwide. Everyone starts tracking the object frantically to refine the orbit. Within a week, that 10% probability will either drop to near zero, phew, false alarm, or it will climb. Let's say it climbs to 40%. Now, you have a serious problem. The Planetary Defense Coordination Office convenes an emergency meeting. They brief the White House, the United Nations, and space agencies worldwide. Engineers at NASA and ESA start running simulations. Can we launch a deflection mission in time? The answer, with current capabilities, is probably no. 8 months is simply not enough time to design, build, test, fuel, and launch a spacecraft capable of intercepting a fast-moving interstellar object. So, what do? you activate emergency protocols that have never been tested in a real scenario. You evacuate projected impact zones, but the uncertainty in the trajectory means you might be evacuating the wrong continent. You mobilize disaster response resources. You hope the probability estimate is wrong, and it misses. That is the scenario we are not prepared for. And the frustrating part is, we could be prepared. The technology exists, or is within immediate reach. What is missing is the political will and funding to build the systems before we need them. Because once you need them, it is already too late. Here is the philosophical question underneath all of this. How much should we spend to prevent a catastrophe that might not happen in our lifetimes, or our children's lifetimes, or even our great-great-grandchildren's lifetimes? Is it responsible to invest billions now for a threat that might not materialize for millennia? Or is it irresponsible not to, knowing that eventually, on a long enough timeline, the threat is mathematically guaranteed? The asteroid that killed the dinosaurs did not give them a choice, but we have one. The question is whether we will make the right choice before a clock starts ticking that we cannot stop. And speaking of clocks ticking, December 19th is approaching fast, when 3I Atlas makes its closest pass. Scientists around the globe will be watching with every available instrument, collecting data that might, just might, help us prepare for the day when an interstellar visitor isn't just passing by. So, what happens after December 19th, when 3I Atlas completes its flyby and starts its long journey back into the darkness between the stars? What comes next for the object itself, and what comes next for us? Let's start with the object's future. After its closest approach, 3I Atlas will continue accelerating as it heads away from the Sun, picking up speed as solar gravity gives it a final, powerful gravitational assist. By the time it crosses Neptune's orbit sometime in late 2026, it will be moving even faster than when it arrived, carrying momentum permanently borrowed from our Sun's gravity well. And then, it simply keeps going. It will pass the Kuiper Belt, past the heliopause where the Sun's magnetic influence fades to nearly nothing, and cross back into the true void of interstellar space. Within a decade, it will be too faint for even our most powerful telescopes to detect. Within a century, it will be light years away. And within a few thousand years, it might encounter another star system entirely, some distant sun with its own family of planets. And maybe, just maybe, astronomers there will spot it and wonder where it came from, exactly as we did. The thought experiment gets wild when you follow it all the way through. 3I Atlas could be traveling for millions of years before gravity from another star significantly alters its path again. It might pass through dozens of star systems during that time, a cosmic wanderer witnessing the birth and death of worlds, carrying with it chemical fingerprints from the star system where it formed. It is a message in a bottle that nobody can read unless they happen to be looking at exactly the right time. But for us, the story does not end on December 19th. In fact, that is when the real work begins. Every terabyte of data collected during the flyby needs to be analyzed, cross-referenced, and modeled. Teams of researchers will spend years extracting insights from those observations. Doctoral students who are undergrads right now will write their entire theses on 3I Atlas data. Scientific papers will be published well into the late 2020s, analyzing everything from surface composition to outgassing patterns to subtle trajectory perturbations. And here is what makes this specific event particularly valuable for science. 3I Atlas is our third data point. In science, you need multiple examples to establish patterns. One data point is an anomaly. 2 data points suggest a possible trend. But 3 data points? Now you can start doing real, Comparative analysis. Oumuamua was weird. The acceleration, the elongated shape, the lack of visible outgassing, we couldn't explain it fully, so some conclusions remained speculative. 2I Borisov was more normal. It behaved largely like a comet, outgassed predictably, and fit our existing models reasonably well. But it was still just one typical example. Now we have 3I Atlas, which seems to be somewhere between the two. It is outgassing like Borisov, but showing unexplained acceleration like Oumuamua. That is scientifically golden, because it suggests there might be a spectrum of interstellar object behaviors, not just two distinct categories. Dr. Michelle Bannister, a planetary astronomer at the University of Canterbury who has studied multiple interstellar objects, said in a 2023 lecture, "Every interstellar object we detect teaches us something, not just about that object, but about planetary system formation across the galaxy." And she is absolutely right. When you study 3I Atlas, you are not just learning about one rock. You are learning about the conditions in another star system, billions of miles away, conditions that created and ejected this object in the first place. Think about what that means for exoplanet research. We have discovered over 5,000 exoplanets as of 2024, but they are all light years away. We can measure their size, orbital period, and sometimes their atmospheric composition if we are lucky, but we will never visit them. We will never hold a piece of them in our hands. Interstellar objects are the closest we will ever get to sampling another star system directly. Every molecule of gas released by 3I Atlas is a piece of physical evidence about chemistry happening around a different sun. There is also the question of detection improvements. Every time an interstellar object passes through, astronomers learn hard lessons about how to spot the next one earlier. After Oumuamua, survey telescopes updated their search algorithms to flag objects with hyperbolic trajectories more quickly. After 2I Borisov, they refined the criteria for distinguishing interstellar comets from long-period solar system comets. And after 3I Atlas, there will be another round of software and hardware improvements. The Vera C. Rubin Observatory and its Legacy Survey of Space and Time, LSST, is scheduled to begin full scientific operations around 2025. This is a game changer. The LSST will photograph the entire visible sky every few nights with a camera so sensitive it can detect objects 100 times fainter than current surveys. Researchers estimate that once LSST is running at full capacity, we could be detecting one interstellar object per year, maybe more. Instead of 3 objects in 8 years, we could have dozens within a decade. What precisely will we learn from these dozens of potential new detections? We will be looking for fundamental patterns. We need to identify patterns in composition to see if interstellar objects from certain regions of the galaxy possess distinct chemical signatures. We need to map patterns in size distribution to determine whether most of them are small, or if there is a significant population of larger bodies we are just not detecting yet. And perhaps most importantly, we will look for patterns in trajectory to see if they are arriving from random directions, or if there is specific clustering that suggests common origins. And here is the really exciting possibility. With enough detections, we might be able to trace some of them back to specific star systems. Right now, we cannot definitively say which star 3I Atlas came from, because the uncertainties in its trajectory grow exponentially when you calculate backward over millions of years. But if we detect an interstellar object early, track it with high precision throughout its entire passage, and it happens to be relatively young, say, only a few 100,000 years into its journey, we might be able to pinpoint its origin star. Imagine that. Imagine being able to say, this object came from Tau Ceti, or this comet was ejected from the planetary system around Epsilon Eridani. Suddenly, you are not just studying a random rock. You are studying a physical sample from a specific star we can point telescopes at and observe. You could compare the object's composition to the star's spectrum and learn about planet formation conditions in that exact system. Some researchers are even proposing missions to intercept interstellar objects. Not 3I Atlas. It is moving too fast and we do not have the technology ready. But a future interstellar visitor detected years in advance could theoretically be reached by a fast spacecraft. In 2019, the Initiative for Interstellar Studies proposed a mission concept called Project Lyra, which would use gravitational assists from Jupiter to accelerate a probe fast enough to catch up with Oumuamua. They calculated it was just barely possible with current propulsion technology, though it would require a decade of flight time. The idea is not as crazy as it sounds. If we can detect an interstellar object 5 or 10 years before it reaches perihelion, the closest point to the Sun, we could potentially launch a spacecraft to rendezvous with it, either during its approach or on its way out. A probe equipped with cameras, spectrometers, and maybe even a sample return capsule could provide data that is impossible to get from telescopic observations alone. You could map the surface in detail, measure its density by analyzing how the spacecraft's trajectory is affected by the object's gravity, and maybe even land on it. The engineering challenges are immense. Matching velocities with something moving at 30+ kilometers per second is no joke, but it is technically feasible, and the scientific payoff would be extraordinary. NASA and ESA have both commissioned studies on rapid response missions to interstellar objects. Specifically, ESA's Comet Interceptor mission is already being built to park in space and wait for a pristine comet or interstellar object to pass by. Now, let's talk about the public reaction side of this. Every time an interstellar object is discovered, there is a wave of media coverage. Some of it is accurate, a lot of it is sensationalized. Headlines scream about mysterious alien visitors and objects defying physics. Social media lights up with speculation, and inevitably, someone suggests it is an alien spacecraft. Here is the thing. It is almost certainly not. The Oumuamua alien hypothesis got a lot of attention because Avi Loeb is a prominent scientist, and he made serious mathematical arguments for why it couldn't be ruled out. But the vast majority of astronomers remain unconvinced. Extraordinary claims require extraordinary evidence, and the fact that we cannot fully explain the acceleration is not the same as concluding, therefore, aliens. But the public fascination with that possibility is actually useful. It gets people interested in astronomy. It gets them asking questions. And if that interest translates into support for better funding for detection systems and planetary defense, then honestly, the speculation serves a purpose. What we need is science literacy, helping people understand what we know, what we do not know, and how we go about figuring things out. 3I Atlas is a perfect teaching moment. It is real, it is happening, and it is accessible. Anyone with a decent telescope can potentially observe it during the flyby. Schools can organize viewing events. Universities can host public lectures. It is an opportunity to engage the next generation of scientists and space enthusiasts. And that brings us to the bigger picture, because beyond the specific story of 3I Atlas, beyond the data and the detection systems and the planetary defense budgets, there is a philosophical question worth sitting with. But beyond the specific scientific data, 3I Atlas forces us to confront a much larger philosophical reality. What does it actually mean to live in a universe where objects from other star systems can physically visit us? For the vast majority of human history, we operated under the assumption that our solar system was an isolated bubble. The sun, the planets, the asteroids, the comets. We believed everything here was born here and stayed here. We viewed the solar system as a closed loop spinning through the void. We knew intellectually that other stars existed, of course, but they were so impossibly far away that they might as well have been in a completely different universe. There was our stuff, and there was everything else, and we believed the two systems never interacted. Oumuamua shattered that illusion in 2017. Suddenly, the universe was no longer separate. A physical piece of another star system had crossed the unimaginable distance between stars and passed right through our cosmic neighborhood. And now, with the confirmation of 2I Borisov and 3I Atlas, we are realizing that this is not a rare anomaly. It is the norm. The galaxy is interconnected. Matter flows continuously between star systems. We are not isolated. We never were. Think about what that means on a strictly human level. Every single generation before us looked up at the stars and saw them only as unreachable points of light. But you, right now, in your lifetime, are living through the precise era when humanity confirmed that pieces of those distant systems can physically reach us. You are witnessing the moment when humanity's cosmic neighborhood effectively expanded from one star to potentially billions. And here is the profound part. Those interstellar objects are ancient, beyond comprehension. 3I Atlas could theoretically be older than Earth itself. It might have formed 5 billion years ago, around a massive star that has since evolved into a red giant, or exploded as a supernova. This chunk of ice and rock could be a fossil from a planetary system that no longer exists, carrying within its layers the chemical fingerprints of a world that died long before the first single-celled organisms appeared on Earth. When you look at the data coming from 3I Atlas, you are looking at deep time made tangible. Carl Sagan famously said, "We are made of star stuff." He was scientifically correct. The carbon, nitrogen, and oxygen atoms in your body were forged in stellar furnaces billions of years ago. But now we know something even more humbling. There is star stuff from other stars passing through our solar system right now. The iron detected in 3I Atlas might have been created in a supernova completely unrelated to the one that seeded the gas cloud that formed our sun. It is not just cosmic recycling within one star's family. It is a material exchange across the entire galaxy. This realization has massive implications for the origin of life that scientists are only just beginning to grapple with, bringing us directly to the hypothesis of panspermia. Once treated as fringe science, this hypothesis suggests that life, or at least its complex organic building blocks, exists throughout the universe and is distributed by space, dust, meteoroids, asteroids, and comets. It has gained significant plausibility because we now acknowledge 3 critical facts. We know interstellar objects pass through our solar system regularly. We have confirmed that some of them contain complex carbon-based organic molecules, and we understand that certain microorganisms, such as extremophiles, can theoretically survive the harsh vacuum and radiation of space if they are sufficiently shielded inside a rock. Could life on Earth have been seeded by an interstellar comet that crashed here 4 billion years ago? It remains a speculative hypothesis, but it is no longer impossible. Even if panspermia is not how life started here, the underlying principle remains valid. We are part of a galactic ecosystem. The boundaries between star systems are porous. What happens around one star can, over vast timescales, affect the chemistry and biology around another. The universe is significantly more connected than we ever imagined. But let us bring this back down to December 19th, 2025, and what it means for you personally. Here is the takeaway. We are living in a pivotal moment in human history. We are the first generation possessing the technology to detect these interstellar visitors. We are the first generation with the engineering capability to potentially defend our planet from cosmic impacts. And we are the first generation that can realistically plan missions to send our own probes to intercept objects from other star systems. Our ancestors looked up at the night sky and saw gods, omens, and navigation points. We look up and see physics in action, gravity wells, orbital mechanics, and evidence of planetary formation. But there is something both of these perspectives share: a sense of wonder. And 3i Atlas should inspire that wonder, because it represents everything we have learned and everything we still do not know. On December 19th, when this object makes its closest approach, take a moment to mentally visualize what is happening. A visitor from another star, having traveled for potentially millions of years through the absolute cold and darkness, is passing by our planet. It has been lonely beyond imagining. Out there in interstellar space, no sunlight, no warmth, just cosmic radiation and the occasional hydrogen atom. And for a brief, fleeting moment, it is here in our warm, light-filled neighborhood, close enough that we can study it and learn from it before it disappears forever. The scientists watching will be gathering data that helps us understand not just this one object, but the mechanisms of planetary formation across the Milky Way. They will be testing detection systems that might one day save humanity from an actual catastrophic impact. They will be laying the groundwork for missions that could, decades from now, visit an interstellar object up close. This is science in real time, messy, uncertain, collaborative, and absolutely essential. But beyond the hard science, there is something deeply human about this moment. We are fundamentally curious creatures. We look at the unknown, and we want to understand it. We see a mystery, and we build massive telescopes to solve it. 3i Atlas is a reminder that the universe is full of mysteries waiting to be explored. And some of those mysteries literally come to us if we are patient enough and paying attention. So, what happens after December 19th? We keep watching, we keep learning, we keep building better detection systems, faster spacecraft, and more sensitive instruments. Because 3i Atlas is not the last interstellar visitor, it is just the latest. There will be more. If the Vera C. Rubin Observatory delivers on its promise, there could be dozens more discovered within our lifetimes. Maybe one of them will have properties so bizarre that it forces us to rewrite our fundamental understanding of planetary science. Maybe one of them will arrive on a trajectory that is a little too close for comfort, and we will finally be forced to use those planetary defense systems for real. Or maybe, and this is the scientific hope, we will just keep accumulating data points. We will build our catalog of interstellar objects, learning about the galaxy one cosmic wanderer at a time. We will trace some of them back to their home stars. We will intercept one with a spacecraft and bring back samples. We will figure out the mysteries that Oumuamua, 2i Borisov, and 3i Atlas have posed. And slowly, piece by piece, we will understand our true place in the galaxy. Not as isolated inhabitants of one lonely star system, but as active participants in a cosmic community that has been exchanging matter and energy for billions of years. December 19th, 2025 is just one day on the calendar, but it is a day when you will know, really know that we are not alone in the universe. Not necessarily because aliens are visiting, but because the universe itself is visiting, bringing physical pieces of distant worlds to our doorstep. And if you look up that night, even if you cannot see 3-eye Atlas with your naked eyes, you can know it is up there. It is racing past at impossible speeds, a messenger from the depths of space, carrying stories written in chemistry and physics. We are living in the age of interstellar visitors. We are living in the age when humanity learned to defend its home planet from cosmic threats. We are living in the age when the universe stopped being something we just observe and started being something we interact with. That is worth celebrating. That is worth funding. And that is worth remembering when the next mysterious object appears in our telescopes, because it absolutely will. The galaxy is vast and the distances are incomprehensible, but every so often, something crosses that distance and reminds us we are part of something bigger. 3-eye Atlas is that reminder. Pay attention to it, learn from it, and when it is gone, keep looking up, because the next visitor is already on its way.